Okay, we don't have a lot of time, obviously, but that's okay because today is actually not a calculus day. We're out at 10:40. Today is an advanced algebra day. What we're going to do today is we are going to review logarithmic functions, and then we're going to use those tomorrow to figure out derivatives and stuff like that. She's taking the placement test. All right, so I don't know if you remember where logarithmic functions come from. But logarithmic functions were developed to, for you to be able to find the inverse of an exponential function. So if you start with y equals a to the x, and you wanted to find the inverse of that, and this is the speech that I gave you a couple years ago. Here's y equals a to the x. You know that function's inverse is a reflection over the line y equals x, so the inverse would look something like that. This passes the vertical line test, so you know the inverse is a function. But if you go, okay, I'm going to do the old switcheroo here and then solve that for y, there's really no way algebraically you can take the yth root of something to solve that for y, because the y is a variable, it's always changing. So they just created a new function, which is a logarithm. And so when you see log base a of x equals y, what they're really saying is this little number right here, bless you, as the base, to this power over here equals that number right there. So, for example, no, this is better to do some examples. For example, the log base 3 of 81 is what? So what this is asking is 3 to the what power equals 81? And the answer is 4. How about log base 25 of 5? So that is asking 25 to the what power is 5? 1/2. Good, because the square root of 25 is 5, so you have to take a root there. And then finally, log base 10 of 0.001 is again saying 10 to the what power is 0.001? 10 to the thousandth? Oh, no, but that's not the power that we're looking for. 100. No, yes, -3, because if you go 10 to the third power, that's 1,000, but we want 1,000, so 1,000th, so you have to make that negative so that it will go on the bottom, okay? -4? So 10 to the -1 would be 1 over 10, which is a tenth. So 10 to the -2 would, right? So I can't, I have this leash on and I can't really go back very far. Yeah. One person that did what? Yes, if one person could do that in one match, all those scores, what did it add up to? 38. Yeah, that'd be a pretty good score. They might be over par. They might be all right. For girls, that'd be 2 over par. Okay, then here's some things that you remember, properties of logarithmic functions, because they are inverses of exponential functions. So you remember that if you go x to the a times x to the b, the way you do that is you add the exponents, right? Okay, so logs are inverses of that. So that means if you have a log of 2 things multiplied together, you can break that up into the log of the first one plus the log of the second one. Or conversely, if you have the log of 2 things being divided, you can make that the log of the first one minus the log of the second one. And then this is the most muy importante log property of all. This is the whole reason why we mess with logarithms in the first place. If you have the log of a number being raised to a power, then you can turn that into a multiplication problem by putting the exponent there in front. And that's super, super handy because it helps us solve algebraic problems that have the exponent as a variable. So, yeah. Represent. Right. Yeah, something with W's on your, yeah, there you go. Yeah. Okay, so if we wanted to use that to solve some problems, for example, if you wanted to know what the log base 4 of 2 plus the log base 4 of 32 was, you could figure that out directly. You could be like log base 4 of 2 is 1/2 because 4 to the 1/2 power is 2. Might take you a little while to figure out what log base 4 of 32 is though. So it's easier to just say, oh, when I'm adding those logs, I can turn those into a single log by using the multiplication property. And then 2 times 32 is 64. So now I just have to answer the one simple question, 4 to the what power is 64? And that answer is trace. Same dealio here, but even worse. Log base 2 of 80, you can't raise 2 to like a whole number or a rational power and get 80. But if you make this into a single division problem instead, then you go, oh, well, 80 divided by 5 is 16. And then log base 2 of 16 is simple, that's 4. That's 2 to the 4th power is 16. Okay? Yeah, numbers are our friends. Okay, we good here? Can I turn the page?
C.
Okay, then we can also do some limits because I guess I lied to you and it is a calculus class, so we have to do a little bit of calculus. Oh yeah, in a minute. Not right now. So log base a of x, the limit as that approaches infinity is infinity. Because if you remember the graph that I drew on the very first slide, logs are inverses of exponential functions, so their graphs look like this. So it looks like this levels off, but it doesn't really. It's actually increasing forever, ever, just at a very, very slow rate. Okay? And then notice that here we can't have the limit as x approaches negative infinity because this has an asymptote at the y-axis. But you could say that the limit as x approaches 0 from the positive side is going to be negative infinity. Okay? So that's pretty nifty. All right, then natural logs are the same as logs, but what's the difference? Nope, nope. Natural logs are the same as logs except, right, the base of the natural log function is always e. So if you see just like log, what's the base for that if it doesn't say, you're right, so that's base 10. So if it just says log, then it's base 10. If it says natural log, it's always base e. If they want to use something else, then they have to indicate it. So if you take the natural log of e to the x, since those are inverses of each other, the natural log and the e cancel, and you just get x. Same dealio if you take e and raise it to the natural log of x power. Again, the e and the natural log will cancel each other out, and you're just left with x. This, where x is an element of the real numbers. Why is that important? Yo no say. Okay, so for example, find x if the natural log of x equals 5. I found it. It's right there. Okay, next one. No? Yeah, if you want to get it wrong. So what's the answer? Yep, it's just e to the 5th because the base right here is e, and what we got going when we're doing logs, just like we did before, is that number to that power equals that thing right there. So x equals e to the 5th. And you could figure that out on your calculator, or you could just leave it like that. Okay, how about this one? Solve the equation e to the 5 minus 3x equals 10. So what do you want to do first? Right, so we're going to natural log both sides to get rid of the e. So if I take the natural log of 5, or e to the 5 minus 3x, that's going to equal the natural log of 10. Right, then the e and the natural logs will cancel. So that's 5 minus 3x equals natural log of 10. And then we just have to do a couple quick and easy algebra steps. You could, but I'm going to leave it in the natural log form so that I get an exact answer. Yeah, it's always going to be weird decimals. So what do I do to solve this for x? Yeah, so I'm going to subtract 5 from both sides. So 3x equals the natural log of 10 minus 5. Hopefully you understand that this isn't going to be like the natural log of 5. This is the natural log of 10. Figure that out first, and then subtract 5 from your answer. And then divide by negative 3. So natural log of 10 minus 5 over negative 3, which you could figure out on a calculator if you wanted to. Or you could just leave it like that. Okay? I know I'm going really fast, but I am. But it's like a review, so, you know. Got a ways to go yet. Okay, how about if you were asked to express this expression as a single logarithm? How would you do that? It means no addition or subtraction in the problem. Natural log of something. Okay, so you know that when addition is the same as multiplication, so you want to make that as a times b, but we've got this pesky 1/2 to deal with first. Close. You take this and move it and make it an exponent, and then combine them together. So it's going to be the natural log of ab to the 1/2. And it was only the natural log of b that is being multiplied by 1/2, so it is only the b that is being raised to the 1/2 power. Yes, ma'am. Okay? So natural logs, same deal. All right, this is an old formula that's not so useful anymore because your calculators have a way that you can enter a log of any base in there. But back in the day when we didn't, then you could do it this way. So if you wanted to figure out the log of something weird, then you could use this formula to switch it around. So for example, if you wanted to know the log of base 6 of 5, you're like, crap, I have no idea. 6 to the what power is 5? I could do like a bunch of guess and checking, but that would be really annoying and that would take forever. So you go, oh, well, instead, I can change this to the natural log of 5 divided by the natural log of 6, and then I can do that on my calculator. So natural log of 5 divided by the natural log of 6. And then that tells me that it's 0.898. That's what I was going to guess. I wasn't going to guess 0.898. I didn't even really think about it. But like Logan said, we have a change of base thingy now on our calculator. So if you go, what is it? Math A. So I'm going to go the short way around. If you throw that in there, oh, but it's log, not natural log. Yeah, but it doesn't. Oh, no, we wanted log, didn't we? Yeah, sorry, log base 6 of 5. So you could do it. Yeah, gotcha. Sorry. So, and then you get the same answer, okay? So this old formula that used to be more useful than it is now, but if you don't have a calculator that has that fancy chain, well, natural log always has a base of e, and so you have a natural log button on your calculator, so that's NBD. Okay, so we just kind of basically did this, so we don't need to do that again. The limits for natural log are the same as the limits for a logarithmic function because their graphs are pretty much the same. It's just a different base. And so you can use all the fun rules that you used to use to graph those. If I was going to graph the natural log of x minus 2 minus 1, the minus 2 inside the parentheses does what? Moves it to the right 2, and the negative 1 down 1. So it would be, if this is like my original thingy, then it would be like something like that. To the right 2 and down 1. Okay? That was fun, huh? Let's rattle off some quick, whoa, I thought we were done. Okay. Yeah, we're not going to talk about that.
Just a question. Number 2, why really is that wrong? Yeah, I didn't multiply with 2. I did it by 1/2. I don't know why.